Hello, welcome back everyone. I hope you had a good restful break. It's still me presenting, chairing, so Jake Rigby, your chair for the rest of the day today in our final session. Gives me great pleasure to introduce our next speaker, Anthony Lorella. He's from Maya HTT and is here to talk about maximizing performance, intelligent operation of energy technologies using combined data streams. So very much on trend with the topic of data discussion today. So without further ado, over to you, Anthony.
Thanks, Jake. Yes, and thank you everybody for your attention today. As Jake said, bit of a mouthful as far as the topic or title of today's presentation, but if we boil it down, that's exactly what we're talking about. How do we handle data and make it work for us? And I think it's no surprise that this is probably a common topic today. We're going to hear about how we handle it at Maya, basically. First, a little bit about Maya, who we are. Why we're talking about this at Maya. Our main focus is to help organizations with their digital transformation processes. We have years of experience in this, in both providing things like software solutions, but also tailoring those software solutions for an organization's specific goals, as well as providing projects to customize how those are being used and tailor it to the organization. When we're talking about software solutions, we're talking about historically engineering software like CAD, CAE, PLM, if you're familiar with those acronyms, but always in the world of digital engineering and digital transformation. So you can see there on the wheel some of the topics that we have been involved with historically and where we have expertise. On top of that, we have dedicated team of engineers and data scientists that will help deliver digital transformation on top of AI services projects. So AI, IoT, all these types of not so new anymore, but still relatively recent topics is something that we also have a good deal of expertise in and dedicated personnel. So that's Maya in a nutshell, and all of this will come together today in what I'm talking about and how we deliver this in particular for the energy sector. As far as my background, my name's Anthony Lorella, like you heard. My experience is in actually mechatronics across a few industries. I've been doing that for Maya for the past 9 years, and more recently branching out into multiple disciplines. I am in Montreal, and I've got a bachelor's from McGill University locally here. So into what we're going to be talking about today, I've got it split up into 3 segments. We're going to first talk about, let's say where we are today or so in terms of the complexity for operations in the energy sector. Then we'll get into how we can use combined data streams and what do I mean by combined data streams to alleviate that. And then we're going to get into a little a case study as far as how our organization can help with this. So starting with the complexity in energy operation. I don't think I need to list these for anybody here, but just to set the topic for this discussion, there's a lot of major critical points that I could get into. I've got a non-exhaustive list here. Things like weather variability, which we've seen recently, has a big impact. Rising pressure for reducing OPEX, always present. Need for higher efficiency, you could probably roll that up into OPEX. Same thing for keeping installations alive for a longer time. You want to get your ROI on your equipment. And then also things like usage and data, complexity in operational data. How do you deal with it? Where does it go? How do you track things? And what do you do once it's tracked? And then things like unpredictability and energy demand. That one can really be closely tied to the first one of weather variability. At the end of the day, all of this will result in, in terms of if it's not handled properly, siloed data that doesn't get used, delayed decisions, suboptimal planning, at the end of the day, lost revenue, lost potential. Tie that into projected estimates. This is a little bit of an older estimate, but it was, I think, around 2012, 2013. estimated that there is about $38 trillion of investment required if we are to meet projected energy demand for 2035. That's not how much money is earmarked, but that's how much money at least one study estimated we need to invest to meet demand. An example of growing complexity and the effects. In this case, we're going to talk about a wind farm and something called wake blockage. There are examples, and you can go find even the one that I've got here, of organizations having to downgrade what they would assume is the optimal or the nominal output of a wind farm on account of things like weather variability, the effect on the annual energy production of the wind farm. And this, as you can imagine, has a devastating effect in terms of not just the value or the ROI statement or the basically the revenue for the organization, but also in the energy production that this is meant to deliver, which has to be severely downgraded. So these are the types of issues that if we had better predictive models and better use of data, we could prepare for and be able to adapt to, even if we didn't necessarily know this particular, wake blockage event would be an issue here. Going a little bit further, we could talk about the variability based on region where we're going to deploy our resources. Things like solar and wind are going to vary, and we have to be able to take that into account as well, and projected estimates for the potential for that energy. How do we do this? So in this case, we're going to talk about how to make good use of data coming from multiple sources and blend them together to help them work for us. In this case, when I say combined data streams, I'm talking about bringing together information from things like sensors, weather forecasts in this particular case, or other up-to-date sources of information, and predictive models. This allows us to get a clearer, reliable picture to make better informed decisions. So for example, if we just look at sensor data, you only know what's happening right now for your equipment. If we only look at weather, we only know what might happen, let's say, tomorrow. If we just look at our physics models, we only have an idea of how an optimal system would be behaving. But if we put it all together, one can inform the other, and we have a fuller, more reliable picture of what we're starting to look at something that will resemble what we call a digital twin. Why is this useful? Well, better forecasting, because now if we combine weather and models, we can calculate how a particular change in the weather will affect efficiency. In this case, I've used a turbine. It can help for automation. We'll talk a little bit about these digital twins as an executable digital twin. But that will help us do something like model predictive control. At the end of the day, this is helpful for reducing cost, improving efficiency, and extending the life of the assets. An example, so going back to the wake and blockage issue. Model predictive control, like I just mentioned, using an executable digital twin, that is a physics model that can run in real time to be able to be predictive, can inform intelligent controls to, for example, adjust the pitch and position of these turbines to minimize that wake and blockage coming from, in this case, if we had turbine control at the field level. Now, again, this comes with the requirement of proper planning in the upstream, not to use a flow pun, but if we do the proper planning and we have the right mechanisms to use this data, then we are ready when unpredicted or otherwise unpredictable events occur. And they help us improve performance, mitigate risk, dampen losses and things like that. At the end of the day, this is just one illustrative example. I can get into something a bit more detailed as to how we would help do this with all of the expertise that I did lay out before. So in this case, we can look at maybe a bit of a deeper dive case study. In this case, we can look at a system that might have, a lot of complexity to it, combined solar, wind, and wave energy production approach. Um, so in this case, what we're talking about is, like I said, a combined wind, solar, and tidal system. In this particular scenario, we can imagine there is the necessary telemetry fitted to the assets, and we have a stream of weather data coming in for that is going to be relevant for all of them. We can imagine this is deployed in an environment where all of the weather conditions are highly variable and the forecasts are unreliable. The idea here is that we really have a requirement, although maybe we can reconsider where we deploy these assets. They are where they are, and we need to identify when operation is going to be a net positive for us, considering multiple factors. Right? We can look at where, we can look at the energy demand at any given time, as well as the projected weather conditions, however unreliable they may be. So the Maya approach, how we would do this, like I said, we can blend together our expertise in engineering simulation, developing those, as I write here, physics-based high-fidelity simulation models. Those alone, and this speaks to the extendability or the life of the usability of these different things, right? Those high-fidelity simulation models alone are helpful in early project lifecycle when we're looking to make predictions as to how things are going to be behaving, and how they will inform the overall design. But they can extend their use for us and becoming also a tool that will inform, um, you know, um, a more live and recurring um, model in terms of being able to combine that. You can see here with things like weather forecast, predicted energy costs, and being able to make decisions on operation based on that data, including the physics-based simulation model data. So now we're not just talking about design and ideal behavior, but we're talking about influencing the operation and day-to-day. At the end of the day, the last piece of this puzzle would be also to have that data come back and influence the actual automation or operation of that equipment by using model management and some form of automation. So if we're talking about, for example, communicating back with PLC or any kind of automation hardware, that would be the last part, the last layer in terms of closing the loop for this digital twin. So when I talk about those physics models, that's again one of the expertise for Maya. We have experience developing models and tailoring solutions on top of these models for customers across multiple industries. So these could be highly complex models. They can be very basic models. There are ways to take advantage of both of these here through mechanisms like model reduction, for example. So a lot of what I'm showing here might be a bit too computationally expensive to run in a continuous loop for something like what I just showed, but there are mechanisms today that we also have mastery of that allow us to make use of these models, like I said, even if they need to run faster than they normally do. So again, physics models, something that is one part of the puzzle. When we do use those as part of an operational loop for the digital twin of operation, we're now talking about something called an executable digital twin. There's a number of different applications for that, such as health monitoring, predictive maintenance, and just basic performance analysis to understand how equipment should behave versus how it is actually behaving, and if we have any kind of anomalous data coming back. Operational data I can categorize into two parts. We can call this operational data coming from telemetry, so any kind of sensors that are fitted to the equipment, or we can say that there is that weather data that's coming back to us as well that we can parse and use as part of the model. For this, we also have expertise in making sense of data. Our data scientists obviously are used to working with large amounts of bulk data and making sense of that to go back and inform that operational digital twin, for example, or to do a number of other things with it. In this scenario, that would be the application. So again, this is already considering a combined data stream of some real sensor telemetry data and some forecasted weather, and in this case, actually also load related information. What this allows us to do when we blend all of this together. So we have that true digital twin of the operation of the equipment that will inform us, and if properly deployed, will be able to correct itself in terms of how it should be behaving based on certain objectives. So here I've got a few scenarios. For example, if a sudden heat wave reduces the efficiency, we can see that with a physics-based model. We can understand how temperature evolution will affect the efficiency of something like the PV cells, the photovoltaic cells. We can also blend that with a projection of increased load, because a sudden heat wave is usually met with increased load on the grid. And if that were to affect us, well, those are two negatives when that combine into a feedback loop, which is reduced efficiency and increased load. On the flip side, a drop in temperature would be impactful for the turbines. We could have, for example, a model that would be predictive of when we would be in a regime where frost could be at risk of forming on the turbine blades and severely impacting performance. Going back to wake and blockage, we can look at sudden change in wind direction, intensity, as well as predicting wear on equipment through ocean data. So we had the tidal system. If waves pick up periodicity or amplitude, that's a net positive for energy production, but what does it mean for wear? So we have to think about what the overall net positive is in terms of ROI of this equipment. At the end of the day, what you see on the right is what we're really striving for. Less consumption, better efficiency, reduced OPEX, increased AEP, and maximizing equipment life. If we wanted to get fancy, we can consider extending to the grid as well, like I said, to look at when peak loads would also be influencing the system. To sum it all up, these combined data streams are important because they are what are going to feed our operational digital twin. The pairing of those combined data streams and the operational twin that I mentioned are the optimal, I would say, approach to being able to take advantage of that data. And this allows us to get, like I said, a clear, reliable picture for making those decisions. So I think that's everything for today. I appreciate everybody's time. I think we have some time for questions now.
Brilliant. Yes, thank you for a great presentation. And yes, we do have time for questions. So if you haven't already, please make sure you add your question to the Q&A section. I've got a few to get us started, and great to continue to pull on this thread around data and how that helps to inform decision making. We talked a bit earlier in the day around the kind of importance of data governance and making sure that you get the right data and you don't have false data coming in or an accurate piece. But what happens, linking to what you've been talking about today, if you have different data sources that don't agree with each other? So if one model says one thing, but the sensors in the field say something else, how do you know which one to trust? How do you get an insight from conflicting data?
Yeah. So conflicting data is tricky, but it's actually part of the end result, because that allows you to take a second and evaluate what's coming in. If you only rely on one source of data, you have nothing, well, to compare it to other than your common sense. But that is what will play a part in this loop overall. someone who understands what that data looks like is going to be an important piece of the puzzle, as well as relying on historical data, right? So if you have a log of what that data looked like in the past, you can understand if things are following a trend or if something is, an anomalous data set that should be thrown out. So comparing data against each other is important to understand if something doesn't look as it should, and then going back in the data history to be able to look back at how it behaved is also critical.
Okay. I get a quote that always sticks in my mind from Amazon, from I think it was Jeff Bezos, the main man himself, was around how they, when they're originally forming, they were kind of pulling in as much data and information that they can, and then afterwards kind of working out what to do with it. Which it sounds brilliant, sounds amazing, but it's a real luxury to a lot of people where the more data you put in, the more expensive it can get. So I wonder if you had any thoughts around how you select the right information and data streams. If you kind of you understand that you've got some elements coming through, you understand there's some elements missing to get the insights that you want.
Mm-hmm.
How do you pick up the right extra threads?
Yes. At the end of the day, I think the number one requirement here is understanding what you want your end result to be. It's to a degree working backwards. So we need to understand, going back to that example, what we want to get out of the digital twin of the operation, right? Because you can say, oh, I want a perfect replica of how the system will operate, which is fine as an objective, but what is it doing for you, right? If we are in a system where we know that there's unknowns based on weather data, then we need to make sure that we cover our bases in terms of weather data, and have a complete picture. But at the end of the day, it really is understanding what you're trying to produce at the end. There is I guess there is an easy a tendency to just collect or amass as much data as possible and then figure out what to do with it later. But some intentionality can help streamline that process in the beginning.
Cool. I like that final comment because although I do like the Jeff Bezos quote, I do think it's quite a dangerous precedent to set, and it sets unrealistic expectations in some areas. So yeah, great. Very quick final one then. With so much kind of data coming in and multiple streams, how do you decide which elements should be processed immediately on site, or how much should be sent to the cloud without adding any extra costs?
Yeah, so I think this kind of goes back to what we were just talking about in terms of if you've got large amounts of bulk data. I think we need to be able to confidently be able to identify which data is immediately actionable, what we need to be as part of our digital twin of operation, and that is usually something that's more useful on site. You can think of, for example, something like the GPS on your phone having positional data. That's something that's immediately actionable data that you want to have access to. If we're talking about longer time scales, longer term data, like the historical operation that I was mentioning before that we have to go back to, that is something that could be cloud based, that you only go back and reference in fixed intervals or at larger time scales. That usually is a good let's say differentiator.
Amazing. Thank you. Thank you very much. I think, great presentation. That's it for time on this session, but thank you very much to our speaker and to all the attendees as well.
Thank you.
Great. Thank you again.